Today, we're going to continue looking at patterns of repeated operations, specifically repeated addition, which will make a linear function, or repeated multiplication that will make an exponential function. This is going to tie all the way back to the beginning, where we talk about multiplication as repeated addition. So that's why the repetition shows up as multiplication in a linear function. And exponents are repeated multiplication, and so that's why exponents show up in the repeated multiplication problems. I like to run linear functions and exponential functions side by side because they're very closely related. They're both patterns with a repeated operation. And I like to focus on a table, looking at the numbers in a table and how we read the table, the sentence that we write to describe what's going on in that table, and the equation that we write, which is the translation of the sentence from English to math. So that's what we want to look at today. And we're going to start off with two similar looking functions. Notice that the two functions that we have here start off at 24. Remember our start, even though the functions go on forever in both directions, if we have a point where x is equal to 0, we consider that as the starting point. That's our middle. So both of these functions start at 24. And the next point on both functions is 512. That doesn't indicate much of a repeated pattern. Are we subtracting 12 or are we dividing by 2? But then we go on to the next point where we have 10. And in the function on the left, it's dropped down to 0. Whereas in the function on the right, it's only gone down to 6. And then at 15, that really confirms what we're looking at, because a 0 has dropped down to negative 12, and then the 6 has dropped down to only a 3. So we see both functions have the same starting point, and both functions have steps that are 5 units long. So here are the similarities. They both start at 24. So if we write a sentence to describe what's going on here, we would say y equals 24 when x equals 0. That's our starting point. In both functions, that's how we would start our description. Here is a fixed point to start with. We'll also notice that the step size in both is 5 units. In both examples, or in both of these functions in this example, the step size for both is 5 units. So something is happening every 5 units. But what's happening every 5 units is different. That's the difference between the two. We don't see it in the first 2 points, 24 to 12, 24 to 12, but we see it in the overall pattern, 24 to 12 to 0 to negative 12. It looks like here we're subtracting 12 each time. There we go. Whereas in this one, we're multiplying by 1/2. We can think of dividing by 2 or multiplying by 1/2. We want to default to multiplication. So if you think dividing by 2, change that to multiply by 1/2. Divide by 2 is the same as multiply by 1/2. So in both cases, something is happening every 5 units. That's a similarity. The step size is 5 units. But in the left function, we see y is decreasing by 12. That's how we'll say negative 12 in a sentence. We'll say y is 24 when x equals 0, and y is decreasing by 12 every 5 units. In the function on the right, we see that what's happening over and over again is multiplying by 5. So we'll say, and y is multiplied by 0.5 every 5 units. Once we have a sentence describing what's going on in the equation, going on in the function, we can write an equation that says the same thing, and we can format it in the same way. We could say our equation is going to start off by saying how y is related to x. So we'll start off y equals, and in both cases, y starts off at 24. So in both cases, we're going to say y starts off at 24, and then we do something to it. On the left, what we're doing is we're decreasing by 12. So let's subtract 12. Let's say decreases by 12. Whereas on the right function, we're going to say y is multiplied by 0.5. So I'm going to say multiplied by 0.5. On the left side, we're going to subtract 12 a bunch of times, but specifically every 5 units. So to say every 5 units, we don't say 12 times just x. We say 12 times x divided by the step size. And we put that in parentheses. And repeated addition is multiplication. This is not how we would write a linear function. That is not the traditional way to write a linear function. This is just the way that I see it when I see this particular table. Start at 24 and subtract 12 every 5 units. And that's what this is telling us. Start at 24 and subtract 12. To say every 5 units, we take x divided by 5. That makes steps equal step size of 5 units. And so in the parentheses is how many times we're subtracting 12. And in the in-between stuff, that would be some fraction number. So x over 5 is the number of times we subtract 12. And it's multiplication by the negative 12 because repeated addition is multiplication. Over on the right, same thing is happening. Something is happening every 5 units. So we start off at 24. What we're doing is multiplying by 0.5, and we're doing this every 5 units. So we make our step size, the number of times that we multiply by 0.5 is going to be x divided by 5. That's where the step size shows up. And we put that in parentheses just like we did before. But since this is representing repeated multiplication, we use an exponent. Exponents for repeated multiplication, multiplication for repeated addition. Multiplication is for repeated addition. Exponents is for repeated multiplication. X over 5 is the number of times that we do whatever it is we said we're going to do. X over 5 is the number of times we either subtract 12 or multiply by 5. So x over 5 x over 5 is the number of times we subtract 12. X over 5 is the number of times we multiply by 5. So in that sense, we're just changing the operation in that's the thing that's happening. In both equations, we say start off at 24 and do this number of times. On the left example, do this is subtract 12. We're doing a repeated addition, so we use multiplication, and we multiply by the number of times we subtract 12. On the right side, the thing that we're doing is multiplying by 1/2, And we use an exponent because the number of times we're multiplying by a half is x over 5. X over 5 is the number of times we do whatever we're doing. X over 5 is the number of times we do the thing. Which is either subtract 12 or multiply by 0.5. The reason that we would want to write the equation is that, oh, yeah, that's fine. Let's leave it this way. Now I should make a note. We don't normally write linear functions this way. We normally summarize with a rise over a run. So we don't usually write linear functions like this. Because the 12, the x, and the dividing by 5, the 12, the x, and the 1/5 are all being multiplied, we can rearrange the multiplication. We would usually summarize the rise and the run as one number, the slope. So the normal way to write this would be, say, y is equal to 24 minus 12 over 5 times x. We usually combine the rise and we usually combine the rise and the run into one number called the slope. Where slope is equal to the rise over the run. So normally what we do is combine the rise and the run into one number, which we call the slope. This is because we can do this with linear functions. But we can't do this combination of rise and run in an exponential function, because I have x is being divided by 5, but the 0.5 is being raised to this quotient. So I can't just rearrange things. This is just a 12 times an x times a 1/5, and I can do that in whatever order I want. I can take the 12 and divide it by 5 first, and then multiply by the result by the x. But we don't have that option with an exponential function. All goes back to the way that operations work. This is not some funky rules that we're making up to torture algebra students. We have plenty of other ways to perform psychological torture on teenagers. We don't need algebra to be adding to that. This is just how numbers work. And this was decided that would be the convenient way. The slope is what's happening every 1 unit to help fill things out a little bit. So normally we would write this as 24 minus 12 over 5 times x, rather than 12 times x over 5. But I like to think of the x over 5 because it thinks of the number of times we do the thing. Because I like to think about linear functions as patterns of repeated addition, and exponential functions as patterns of repeated multiplication, and I like to look at them at the same time. Let's talk about how we can use the equation part to get the stuff that's not in the table. We want the equation to find stuff that's not in the table. We want to be able to extrapolate what's going on or interpolate what's going on, depending on whether we're looking inside, in between the data that we have, or outside the data that we have. But what we want is we want the equation so that we can find stuff that's not in the table. So we had these equations. Both started off at 24. On the left equation, we subtracted 12 a bunch of times, where on the right equation, we multiplied by 1/2 a bunch of times. Since this is repeated addition, we used multiplication. And since on the right we had repeated multiplication, we used an exponent. And then we multiplied by, in the linear one, we multiplied by the number of times we subtracted 12, which was x over 5. On the right function, we made the exponent the number of times we multiplied by 0.5. And so we raised to the x over 5. Where do we start? What are we doing? How often are we doing it? Y is 24 when x is 0, and y is decreasing by 12 every 5 units. Y is 24 when x equals 0, and y is multiplied by 0.5 every 5 units. So we want the equation to find the stuff that's in the middle. What if we needed, that's not in the table? So what if we needed to know what's going on in both functions when x equals 3? So when x equals 3, y is equal to 24 minus 12 times 3 over 5. What color did I not use? I used all the colors. Can't really tell the difference between the blue and the black on the scans, but trust me, that 3 is in blue. In the exponential function, we would say times 1/2 to the 3 over 5. We can work this out by hand, but why would we do that when we're armed with calculators? Let's see. And also, if we're on a desert island and we don't have our calculator, we're probably not doing math like this. We have other concerns. So I never bought the desert island argument. I also don't like using the, I can't remember what Texas Instruments call it. It's the math print version. I like it. I like keeping my calculator in Classic because Classic forces us to learn single line syntax, and single line syntax forces us to actually understand what the operations are, even though all I have to do is type exactly what I wrote. So it's 24 minus 12 times 3/5. So what I'm doing is subtracting 12 3/5 of a time. And that'll be 16.8. So y equals 16.8 when x equals 3. But on the exponential function, I would say 24 times 0.5 to the 3 over 5. Let's round to the nearest tenth, so 15.8. I usually go for thousandth for random reasons. I just picked thousands because it was kind of convenient usually, and you're not going to guess your way to the thousandth. So we'll say y equals 15.834 when x equals 3. Questions? What we care about is how things change. So here we looked at the difference between changing the operation. On the left, we had subtracting 12 a bunch of times, and on the right, we had multiplying by 0.5 a bunch of times. What we want to be able to do is look at how things are changing. So one of the things that we're concerned with when we're studying things from a perspective of the rule of four, we want to describe something in four different ways: table, sentence, equation, and graph. But we also want to understand the relationships between the different descriptions. If we make a change in one of them, how does that affect the other descriptions? How does a change in one of the descriptions affect the other descriptions? So changes in one description make changes in the other descriptions. Changes in one description lead to changes in the other descriptions. So for example, let's suppose that where we started was true. So let's suppose that y is equal to 24 when x equals 0. That is still a good starting point. And let's suppose that we change this to y is decreasing by only 11. And this is still happening every 5 units. So this changes how we would write the equation, but only in how things are changing. We would say y starts off at 24, and now we're going to say decreases by 11 every 5 units still, so still going to multiply by x over 5. It's still repeated addition and subtraction, so I still summarize with multiplication, and this is still happening every 5 units. The traditional way to write this would be 24 minus 11 over 5 times x. Actually, it would be minus 11 over 5 times x plus 24, because traditionally we like to write things backwards. But I like my equations to match what I write in my sentence. And we can also read this description and quickly come up with a table of values. We start off at 24, and we subtract 11 every 5 units. So after 5 units, we'll subtract 11 one time. So we'll end up with 13. After 10 units, we've subtracted 11 twice. We'll be at 2. And then at 15, we'll subtract 11 a third time and being at negative 9. If we change where things start, if I said y is equal to, looking back, it wasn't actually starting off at 24. It was actually starting off at 32. So y equals 32 when x equals 0. And y is decreasing by 11 every 5 units. We can write an equation. It's still decreasing by 11, but now we're starting off at 32 rather than 24. So 32 minus 11 a bunch of times. We're subtracting 11, so the repeated operation is multiplication. And this is happening every 5 units. In our table of values, we want to see how it would look different. Instead of starting off at 0.24, we'll start off at 0.32. 5 units later, we'll have subtracted 11 from y one time, so we'll be at 21. 10 units later, we'll subtract 11 a second time, and we'll be at 10. And 15 units later, we'll subtract 11 one more time and be at 1. Negative 1, excuse me. So in this case, I changed the description in the sentence. We use the sentence to write a new equation, and we use the sentence to write a new table to give some sample values. If someone came along and said, well, what's going on in this left example? If we start off at 24 when x is 0 and decrease by 11 every 5 units, what's going on at 17? We'll just use the equation. We'll say 24 minus 11 times 17 divided by 5 will be at negative 13.4. We can use the equation to evaluate points for points that are not in the table. Or we want to go backwards. What's going on at negative 3? So instead of 17, we'll just put in negative 3. And at 30.6, then we'll decrease by 11, 3/5 of a time, and we'll be at 24. Let's suppose that I write a different equation. Let's suppose that I write the equation y equals 32 times actually I want to use the time symbol. 32 times something weird like 1.5. 32 times 1.5, and let's suppose that we're going to do this about multiplication a bunch of times, so I use exponents to say a bunch of multiplication. And let's suppose that we do this every 5 units still. We want to be able to read what's going on in this equation. In this equation, we see that y equals 32 when x equals 0, and y is multiplied by 1.5 every 5 units. If we wanted to come up with a table of values, to give our reader some samples of what's going on, we'll say, well, start off at 32. And we'll multiply by 1.5 every 5 units. So at 5 units, I'll take the 32 and multiply by 1.5, and that'll be 48. After 10 units, I'll multiply the 48 by 1.5 again, and I'll be at 72. $32 goes to 72 if we multiply by 1.5 twice. If I start off with 32 and multiply by 1.5 twice, we get 72, because that's what exponents are. Exponents are repeated multiplication. And writing the expression 32 times 1.5 to the second means take 32 and multiply by 1.5 2 times. I can even go backwards. I can see what's going on at -5. And to figure out where, if I'm saying what times 1.5 is 32, I can figure that out by going backwards. 32 divided by 1.5 means we must start it off at 21 and a third. Notice if I take 21 and a third and multiply by 1.5 twice, I'm at 48, because 21 and a third times 1.5 once is at 32, 1.5 again is at 48. This whole time I'm maintaining a step size of 0.5. And these are the values I would get if I plug these numbers into my original equation. 32 times 1.5 to the 5 over 5 is 48. 5 over 5 is going to be 1, and that means we're multiplying 32 by 1.5 one time. 32 times 1.5 to the 10 over 5, 72, because 10 divided by 5 is 2. 10 divided by 5 is 2, and we're taking 32 and multiplying by 1.5 2 times. This is the way that I like to learn how to read linear and exponential functions, and the reason that I like to learn these two forms at the same time. We've been examining the changes, we've been examining patterns, functions with a pattern of repeated operations. Linear functions have a pattern of repeated addition. Exponential functions have a pattern of repeated multiplication. We want to be able to describe these functions in 4 different ways. We've been using 3 so far. We want to describe these patterns in 4 different ways: with numbers, with words, with an equation, and with a graph. We've been looking at how changes in one of those descriptions produce changes in the other descriptions. And we've been looking at the same kind of structure. Start at one value of y, a fixed value of y, do something to y a bunch of times. And the x over the step size is the a bunch of times. All right. That's going to do it for today. It's just a matter of going out in the world and looking for examples of where we expect linear functions to happen. Where do we expect adding and subtracting to happen where it's the same amount that we add and subtract all the time? And where do we expect things to change with multiplication? Because we use that one way more often. All right. That's going to be our subject for next time. Where do we see these 2 kinds of patterns? That's going to do it for today. I will see y'all on tomorrow, and thanks for playing.